Cool. So let me ask you guys a question. What is white light?
The absence of, or it's a combination of all.
Yeah, combination of all the wavelengths and stuff like that, at least or so we think. And what happens when you shine white light through a prism?
It changes to its wavelength.
Yeah, it spreads it out to its wavelengths. We'll talk about reflection and refraction at some point here, but it spreads it out and you can see all the different wavelengths. Well, it turns out if you take the white light, say coming off the sun, and you spread it out into its wavelengths, you'll find out that there's certain wavelengths missing. And we see dark lines right where those wavelengths should have been. And it turns out if you take white light and shine it through hydrogen gas and helium gas, and then do the same thing, you'll find out the same colors, same wavelengths end up missing. This is how we know that the sun is made up of primarily hydrogen and helium, because if it's made up of hydrogen and helium, then as light shines through it, certain wavelengths get removed. And it turns out that hydrogen and helium observe only particular wavelengths. So this was kind of a mystery for a long time. So until Mr. Niels Bohr came along. And what Bohr predicted is that electrons would orbit around the hydrogen nucleus in these circular orbits. And if you notice, electron has potential energy associated with it. So the nucleus here has a big fat positive charge, right? Protons there. And the closer you are to that nucleus, the lower the potential energy. Well, what he predicted is that only certain orbits existed. And that way the electron can only have certain energies. There was an orbit here and there was an orbit at this distance, but there was no circular orbit anywhere in between. And we can, talk about centripetal motion. He viewed these circular orbits and said mv squared over r equal to, the force of attraction, Coulomb's law and stuff like that, and derive an expression for this. But end of the day, turns out his model was wrong, right? Do electrons actually go around the nucleus in circular orbits? No, it turns out they go around in orbitals, or they at least exist in orbitals, s orbitals, p orbitals, d orbitals, stuff like that. But it turns out for hydrogen, his math all worked out amazing. Just didn't work for anybody else. It only worked for one electron systems. And as all the other atoms had more than one electron, it didn't work. So it could work for ions that had only one electron as well, but it just didn't work for anybody else as a neutral species. But it worked for hydrogen, and it worked to the T. All the math worked out. You could predict exactly which wavelengths would be missing and stuff like that. And the idea is that this electron could jump out to different orbits, and the amount of energy, the energy difference between the energy of the electron in these orbits would be the amount of energy it would absorb. And it would absorb the photons of exactly that energy. And he came up with a very simple equation to describe the energy of each of these orbits, relating it to what we call the principal quantum number n. And it turns out he just said that the energy of an electron in any one of these orbits and you can express it in electron volts or joules. So chemists tend to prefer joules, physicists electron volts. But you can see there's just a simple equation here for the energy of an electron in any one of these orbits. So if you look at the n equals 1 orbit, what would be the energy of an electron in the first orbit? The first shell, we might say, these days. So negative 13.6 electron volts. What would be the energy of an electron in the second shell? And you don't have to work it out, just give me the math. Negative 13.6 electron volts divided by 4, so on and so forth, or divided by 9 for the third shell, so on and so forth. And so you have this simple equation, and therefore you can come up with a simple equation for the difference in energy between each of these. And so if you look, that equation is also on your handout. You could say delta E is equal to negative 13.6 electron volts, 1 over n final squared minus 1 over n initial squared, and come out with an equation. And it turns out this difference in energy was the energy of the photon that would be absorbed as white light passed through hydrogen in this case. So it turns out it works the other way as well. Instead of going out and absorbing photons, it turns out if you can get photons out there, and you can get them out there by light, it turns out you can also excite them using like electricity and stuff like that. Then those photons might drop back down, and instead of absorbing a photon, then turns out this atom is going to emit a photon. But Bohr explained to a T the absorption and emission spectrum for hydrogen. Again, he struggled with all the other atoms, but he got it to a T for hydrogen. So he can calculate the energy of these electrons and stuff. And so even though his picture here is really wrong. There's no circular orbits, there's s orbitals and p orbitals and d orbitals. What was right is he said that the energy of an electron is quantized. It only can exist at discrete quantities, and that part is still correct. Chris?
So you said a photon's emitted when it's going towards the nucleus?
So, correct. So notice to go from a low energy orbit to a high energy orbit, you got to absorb a photon of light, the energy from a photon. But when you drop down, you actually go from high energy to low energy, so you give off a photon of energy, that excess energy. And the energy of the photon either absorbed or emitted is equal to the difference in energy between what an electron would have energy-wise in the orbits.
So absorb energy in a photon and then...
Yep, absorbing going out, emitting going in. So think about it this way. So as I drop this marker, what's happening to its potential energy? Yeah, it's decreasing. It's attracted to the Earth. When you let something go towards what it attracts, it lowers its potential energy. Same thing, this electron here is attracted to that nucleus. The closer it goes in, the lower its potential energy. And so if you want to go to higher potential energy, it's going to cost you. You're going to have to get that energy from somewhere, from a photon. But if you drop down, rather than costing you, that's where the electron wants to go, and so it releases the excess energy instead.
Theoretically, when you drop the marker, did it release a photon?
Is this marker an electron?
No.
Sweet, you have your answer. So in the marker's case, obviously we're just converting potential energy into kinetic energy and so on and so forth. But in the case of an electron, so that difference in potential energy is either an absorbed photon or an emitted photon. Cool. All right, so turns out the equation they actually came up with, so since the difference in energy, the energy of a photon, is inverse proportional to the wavelength, the actual equation they came up with was having this lovely Rydberg constant looking something like this. And N1 and N2 here, like up here I had N final and initial. So what you should realize though is that N1 and N2, so you can't have a negative wavelength, right? So depending on which value of N is bigger, might give you a wavelength that's negative. Well, you can never end up with a negative wavelength. The way you're supposed to interpret that is if the wavelength comes out negative, that means it's an emitted photon. If it comes out positive, it's an absorbed photon. Cool, but this very simple relationship, the Rydberg constant, RH here, is on your handout. And so with this, oh, these are still supposed to be squared. My bad. So, but you get this very simple relationship, and they could predict all the missing lines, the missing wavelengths from a hydrogen atom with a simple equation. And so now you guys are expected to be able to calculate where these lines are missing as well. So if we look at question number 2 on your handout. So we want to go from the n equals 5 state to the n equals 2 state. And we just want the wavelength of the light emitted. So we can use this equation, or we can go and use this equation. It's really our choice. So this one might be easier to use in this case since what we want is wavelength. But say we wanted the energy of the photon or the frequency, we might have gone this route instead. So, but in this case, so your Rydberg constant's on there again, 1 point.
Just like do 1 over all of that just to solve for wavelength already?
You can, yeah, you can just 1 over the whole thing. Just be careful, that doesn't mean necessarily doing n final squared minus n initial squared, but it's 1 over the entire, this side of the denominator, or this side of the equation. And can anybody get me that wavelength that would be associated with this? And what is that equal to in nanometers? Cool. And what part of the spectrum might this be at 434 nanometers? Yeah, it's probably in the blue-violet region of the visible spectrum. So here's the deal. If we look at specifically the emission spectra, so a lot of different guys examine the emission spectra. So and if you have an excited electron up in one of these higher states, it has some options. It can drop down to shell number 1. And it might have started in 2, it might have started in 3, it might have started in 4, it might have started in 5. And so you get a variety of different wavelengths of light being emitted here by dropping down to shell number 1. Now you could have also dropped down to shell number 2, and you get a different set of wavelengths in that series. You might have dropped down to shell 3 instead, and yet again, you get a different set of wavelengths associated with that. And each one of these was referred to as a series. If you drop down to 1, that's the Lyman series. If you drop down to 2, it's the Balmer series. If you drop down to 3, it's the Paskin series. N equals 4, the bracket series. So I don't know how important those are. One thing that is important here, though, and it's the example I gave you. So notice in this case, by dropping down to shell number 2, what series was that a part of for the wavelength we just solved for? That's the Balmer series. The reason the Balmer series is special is that these lines tend to correspond to visible light for the Balmer series. So if it's n equals 2 here, dropping down to that corresponds to visible light, how would the energy of the electromagnetic radiation for the Lyman series compare to that? So the Balmer series is dropping down to n equals 2, and that corresponds, these lines tend, the wavelengths of light corresponding to those energy differences, those photons tend to correspond to visible light. Now the Lyman series, how would the energy of the photons in the Lyman series compare to those in the Balmer series?
Infrared?
So, well, I'm just in this case, would it be higher energy or lower energy?
Oh, lower energy.
Ooh, they're bigger drops. Notice bigger differences. So they actually be higher energy photons given off.
That's right.
And so what's higher energy than visible?
IR or infrared.
The way around, higher energy would be ultraviolet. So these tend to be ultraviolet, or possibly even X-ray. So whereas if you look at like the Paskin or bracket series, these tend to be in the infrared, much smaller energies. So infrared's lower energy than visible, and UV is higher energy than visible. Cool, so the Balmer's kind of special because it happens to correspond to light that we can see with our eyes. Cool, so something else we can do with this is emit X-rays. Let's take a little bit different approach to emitting X-rays here. So if you take something larger than hydrogen here, and let's just pretend here that Bohr's model is correct. It's an easy model to kind of look at, even though it's not technically correct. But let's just say we got, electrons in these shells, and we got several electrons in a lot of these shells, and all this stuff. So let's say I hit this with a high intensity beam of electrons, and that beam of electrons hits this electron and ejects it clear out of the atom. So that's going to create a hole in the 1s orbital. So, and for the purpose of X-rays, we refer to the 1s orbital here as the K shell. Now that makes these L shell electrons get a little envious. So notice if all of a sudden your boss at a company retires, what does that mean is open? A better position in the company for you and everybody else who wants that position. And so in this case, notice where's an electron have a lower potential energy, in the K shell or the L shell? Shell number 1 or shell number 2? In the K. And all of a sudden, because we knocked that electron out with a high intensity beam of electrons, all of a sudden that position is available. And so this lovely electron from shell number 2 has a chance to drop down to shell number 1. And it turns out for some of these larger atoms, that drop in energy right there happens to correspond to the energy of X-ray electromagnetic radiation. And so this is how we can get certain materials to emit X-rays. We just knock an electron out of the core. We have to have a very high intensity beam of electrons, we accelerate the electrons through a potential difference. It has to be a very large potential difference. That way the electron's got enough energy to knock that clear out of the atom. If it's not enough, then this is gonna happen. Cool, but we can get to emit X-rays, and what are X-rays valuable for? So imaging, so cancer treatments, all sorts of stuff. Cool. X-rays are also useful for one other big thing. Turns out, in an imaging technique, I can kind of see what your body looks like. So underneath, right? So how does that work? Because X-rays, most of them kind of pass through you, but not all of them, especially if what? So, and what's special about bone that they're hitting that might?
It's just denser.
It's more dense. It's got heavier elements in there, like calcium, and even heavier things than that. And so when it hits heavier elements, they're more dense, and so the X-rays aren't as likely to make it through. And so all of a sudden you see a contrast between bone and not bone and things of this sort. And so that's what's going on. If you look, though, X-rays are useful in another sense. Instead of just looking at contrast between ones that make it through and ones that don't, so we can actually shine X-rays through a crystal, And as the X-rays get diffracted, they actually form a pattern. And they've got complex programs now that can take all the scattering of the X-rays through a crystal structure, and they can kind of backwards calculate where all the atoms in the structure are as well. So, and they get crystal structures for even big molecules such as proteins and stuff like that. In fact, at our university, we're fortunate enough to have one of the early pioneers in X-ray crystallography for proteins. He was a month short of being the first and ended up being the second, which means he was a month short of what? Well, just Nobel Prize. You don't get the Peace Prize for, but he was a month shy of getting a Nobel Prize. Kind of a bummer, yep. So, but, so second place, yeah. They give you a red ribbon instead of a blue one, you know? So, but the idea is that X-rays can also be used in their diffraction patterns to kind of elucidate crystal structures. As long as I can get something to fit into a nice repetitive crystal, I can get a structure out of it with X-rays. Cool. Key though is that proteins don't like crystals all that much, and how much those proteins look like what they would really look like, in their native state in a crystal, that's all debatable and stuff like that as well. But we've learned quite a bit of valuable information on protein structure by being able to get these crystal structures.